to another session of the SIMBa seminar. No. Good. Welcome everyone to another session of the SIMBa seminar. Today we have Jordi Daura Serrano, and he is going to talk about the degree of symmetry and the total rank conjecture. Jordi, the floor is yours.
Thank you for the presentation. So, yes, the degree of symmetry and the total rank conjecture. So, the idea of degree of symmetry, it's like we know that the manifolds, more the ones that we are used to, are symmetric. For example, in the case of surfaces, we have the sphere that we know that we have a lot of transformations, like, for example, rotations around one axis or another one. So we say that this has a lot of symmetries. Another surface that we have, for example, is the Toral, that we also have quite a few symmetries because we have this rotation that we also can take and do this type of rotations. So, well, we have already two surfaces that are really symmetric. So we go to higher genus and we see these torus with two holes, and let's think which continuous symmetries we can put here. And the thing is that we cannot make rotations around any of these holes. We cannot make also these rotations. So it's more difficult to find one of these, but that's, we can think, well, we can have involutions, so like symmetries. But these are discrete, and these are, so at least in my talk today, we are not interested in these ones. And indeed, we can try as much as we can, but there's a theorem by there that says that if we have a closed surface with genus equal or greater than 2, then we don't have any symmetries. Yes, this statement is not really precise because I have not defined what is a symmetry or thinking this. So the first part of the tutorial will be introducing the basic definitions or tools of the theory of compact transformation groups. That is the theory that studies this type of problems. So first I will read out some definitions. G is a group. It is a smooth manifold. Group. And also the operations of the group, so the multiplication. The inverse. We will use only the continuous part, but so it's enough to this has to be continuous, but I prefer to work with the group. So although we don't use the smooth thing, we have already this we need. So then a group action of G on X a manifold, or if you want only working in the continuous setting at the topological scale, but we will know that this symbol is a continuous map. which behave well with respect to the group operations that we have in there. So with these two properties that another one that it's okay, so this is the basic object. So for example, in the case of S2, if we see the group G S1, then this rotation is a group action of S1 minus 2. So we have maybe an alternative definition, although I put this as a remark, that maybe it's not clear that a group action is also a map, a group. That goes from the group, in this case, with a group of homeomorphisms. And if you want to have a structure or work with the smooth category or by isometry, you can replace this by, for example, the homomorphism group. Each theory has its flavor. So the thing is that we want to have symmetries, and there's an easy one that if you put that this map also always you have the trivial action that is then this is not really useful. So we always make this restriction that an action will already write. It's effective if in this case of this definition, the kernel of this homomorphism. This means that there's no non-trivial element of the group G that acts like the identity. And in order to study group actions, we have also two other basic concepts that are the isotropy groups and the. So we take any point of the manifold, then we define the isotropy group with the elements of G. Just annotation. I need to write. These are the elements that fix this point. And we also have the orbits, so given X. That are precisely the points. So in the first case, we look at the element of the group that picks one particular point, and the other one we look at the orbit, so where each element of the group sends this point. And we have a relation, so we can define a map that it's called evaluation that goes from the group G to the manifold that sends the element of G to the imaginary orbit. So, well, this is not subjective in general because we can have elements that fix the point. So what we usually do is define a map that goes from the cosec space. We can do this because this is a group and this is a subgroup, although this is also a manifold. That is precisely that. And the thing is, if G is compact, that it will be always the case for us, then this map is homomorphism. So the thing is that we know already how each orbit looks. It would be something like this type of cosec space. And finally, one last definition is that you can see that we have an equivalent relation. In points in X that says that the equivalent we have the same orbit. So with this equivalence, then we have the quotient space that is usually denoted by. So this space is the space of our orbit. So a point here represents our orbit in the space X. So apart from the example that I told you in the different practices, maybe there's other important ones. For example, if we take X and G to be the linear transformation, then we have an action that sends a matrix, and in this case a vector, with a matrix modification. This is called a linear action. Another example that we can describe this action, and if we take X to be the sphere inside Rn and G to be this creates the orthogonal group, so it fits the norm. We also have the same action. Or another example that I like because it's easy to draw, if we take X, the modulus bar, G, 1. So we have the rotation that in this case it's only this translation. So we start, for example, with a point here, we start moving, we reach this point, but we need to continue here below. And then we go up again. So this would be an orbit. The thing is that you see we have these two parts. So if we take a point just in the middle, then we go here, but we get back again. So for each point here, for example, this X, this Y, we have that here the stabilizer is trivial. But next, the stabilizer is in this case Z. So the thing is that if we want to study group actions, we should somehow have theorems that let us see the difference between these two types of orbits. Just one last definition about group actions is that there is another very important type of group action, apart from effective ones that we always assume. That are free group actions. So we have an action. And it's free. For any point that we take, each element of G move this point always. So all the stabilizers treatment. And the importance of these actions will be clear in a moment after I will also tell you what the fiber bundle is, because it's one of the main objectives that we have. So, in this case, fiber G bundle. Because if we are talking about groups, we would like to have group actions in at least here in each definition. So for us, a fiber bundle, it's a map that goes from E to the basis to another. So these are topological spaces or manifolds, although we like to drop the condition of being a manifold because we usually gets things that are not in the case of continuous actions that are not free. So we have F, another topological space, and a group action of this G. Then we say that it's a fiber bundle. The idea is the same in the case of manifolds, so we need to have trivialization. So we have a collection of U phi, where the collection of U over U open sets. So the idea is that we have here our space E that goes mapped to another space B. And if we look at one of these sets, well, we can put it back here. We have the pre-image. And then this set here, it's a product of, here we have it, and we will have an equation to one of the fibers. So the pre-image is in this case homeomorphic to the product. So in this case, phi is a map that goes from So in the case of manifolds, we have that open sets of the manifold goes to the Euclidean space. In this case, we have that goes to a product of a fiber and the base and the open set itself. This combines. And the thing is why we have an action, because this would work, for example, in the case of topological manifolds that we don't have any way to patch chars. This also are called chars. But if we have a group action on F, this gives more of a structure of like a smooth manifold in the sense that we can go back and forth together between chars. So if we have another char with this in this case, then if we make the composition, for example, in this direction, then the map that is of the form P obviously will send a point U very much in that way will not change, but in this case it would be of the form where this map is a transition map that is defined using the group action that goes from the open set to the group G. So this structure that it's quite complicated. There's a special case if F is equal to G, so we have that if the fibers are the group itself, then it's a principal. And the action is by translation. The thing is that, okay, so imagine that we have here it's 4, 5, then imagine that we have another one. So to move at each point, we multiply by another. So it's like the idea of how you can think principal bundles. It's so you have the fiber bundle that you have each group, but you forget where the identity is. So you need to move the identity depending on which point you take. And the thing is that with this, we can define any fiber G bundle using what is called the associated bundle. What it means that we take a principal bundle and we have a Fig space. And then what we do is define an equivalence relation that I do not have time to define here. The thing is that you need to imagine this as we have a free action here, an action here, and we take these two actions and put these together and take the quotient. This it's like a way of attaching attaching each fiber to the group. So we are replacing the fiber. So why all this introduction? It's just to explain what big theorem that has like geometric label. It's a nice theorem. So the idea is that we have, in this case, our manifold n over x, I will use x. We have our compatibility group, I think, on our manifold x. we have x, and we have a point here, and we have an orbit. So the idea is that we have a manifold, so we have charts that helps us to work locally. And the idea here is, what if we can do and create a chart for the orbit? So in a sense, an open neighborhood of this orbit that works fine with the loop action. The thing is that if G is compact, then we can do this. How we do this? Well, the idea is that if this is compact, then this orbit is a submanifold. And we can look at the tangent space here that is divided between the directions that are on this submanifold and then the normal path. And if we take a small neighborhood of this, then for each one here, the orbit will be not for a neighborhood small enough that you can create using exponential map. The orbit would not be too far away. So the idea is that we have then a way to define like it would be better if we have like something that is like a tube. So they cover the orbit well. It says the slice theorem because what it says is that we have this thing here that if you take a tube and take a chord, it's like a slice. And with this, well, I will not have time to prove this, but this is like the basic theorem that we use to prove things geometrically in the case of loop actions. So now about the degree of symmetry. Yes. So the idea of the degree of symmetry is that we want to make a distinction between manifolds that like the sphere that has a lot of symmetries and manifolds like these surfaces with the genus bigger or equal than 2 that don't have any. So the definition of degree of symmetry is like perhaps not really imaginative. Of x, it's simply defined like the maximum number of the dimension of the dimensions of three groups compact G. Which acts on x. So, well, I think that it's a really reasonable definition. We look at all the groups that can, compactly groups that can act on this manifold and say, well, we take the maximum. So, well, first it's difficult to say which compactly groups that acts on an arbitrary manifold. If you give me one, I could not say this. The thing is that, for example, we have theorem. It's a classical theorem like Frobenius and Birkhoff that says that, okay, we maybe don't know exactly which one it is, but this can be bound. By this value. And okay, at least we know something. It's that if you were, sorry, and It's the dimension of the manifold. So a natural question is, if I have the equality here, I can say something about x. And the thing is, yes, and very close, it has a converse. If we have the equality, then the manifold is a sphere. That is the thing that we think that is the most symmetric thing. And indeed, you need to be careful with this because this is really diffeomorphism. For example, another theorem that this case that Xiang says that if x is homeomorphic to an exotic sphere of 5 dimensions, then this index of symmetry is easily equal than it was n squared. So you see here there's in this study.
What is that? N squared or
N, I think it's n, it should be n. Or maybe it's n squared. It's the thing is that you see this it's homeomorphic to a sphere. Well, sorry, I mean that this is smooth. You can make the same definition, but asking the action to be smooth, so on the answer smooth. So you see that there's a difference between the smooth structures that you can put on a manifold that affects the degree of symmetry. The thing is that in this case, more theorem that we can ask, okay, if the manifold is not a sphere, then how big can this be? And I think that this, well, it's from a Japanese guy. A Japanese really studied these topics in the 70s. Wataku. That or either ex is the same, then the degree of symmetry is we have like a whole gap of possible dimension of groups of Lie groups that cannot act effectively in this space. Even more, if we have the equality here, we can say geometrical things like relation with the scalar curvature of this manifold if all of this is things. So the thing is that we can expect that most manifolds do not have a lot of symmetries. And indeed, there's like a conjecture or something that is thought that if we pick an arbitrary manifold, then this number will be 0. So we are not used to having asymmetric manifolds that is called, so that don't have fractions. And maybe 2 important results to obtain them, and it's one that I especially like, and it's something about the smooth manifolds that it comes really from analysis. So all these proofs are more or less geometrical. The next theorem talks more about analysis of X. In this case, it's a foreign in manifold. This is a topological condition that, and we can define a topological invariant that is called the A path, that is defined by a T and Hitzer rule that says that if this is not equal to 0, then this has doesn't have any symmetry. And the thing is that this, for example, it's preserved, well, preserved. It's additive with respect that connects some of manifolds. So one way to get one of these manifolds is to find like an exotic sphere that has this different from zero and can connect it soon with anything that you like. So changing the smooth structure, it's really dramatic in this case, in the case of group actions that preserve that are smooth. And another theorem, in this case by one word, is that there exists a manifold but it means that it's the quotient of here is a discrete group of isometry, so X, well, Euclidean isometry, so it's just a group of the elements here are affine transformations are a matrix and a vector. So we have a compact flat manifold, and the funny thing is the dimension of dimension 141. That's that. It doesn't have any symmetry. So we start with something that has really a lot of symmetries, like the Euclidean space, or if you want to see this as a quotient of a torus by the finite group. And we can find a finite action that its quotient transforms this in something that has no symmetries at all. So the thing is that this is very useful to study. Well, it's a very interesting question. It was really studied in the 1760s. I think there are some papers still published on this type of results fixing that type of manifolds. However, we can have alternative definitions. So another one, well, in this case too, it's the abelian degree of symmetry. So we are only concerned in this case on abelian group actions. So it's like before, the maximum, in this case of the torus TR. And the thing is that effective actions can be really complicated. And if we have free actions, or what it's called almost free actions, then we have more structure in the quotient and it's easy to work. So we can define another of these quantities that is the rank. So it's precisely the maximum of the max. The mix, it should be really almost free, but I cannot define what is an almost free action, so we can stay with free actions. So as before, we can ask for bounds. And we have that with the dimension of x equal to n, then this abelian degree of symmetry is least or equal to the dimension. It's even easier to work in this time. Well, I have not said before in the case of the degree of symmetry that the group that you need to take on the sphere to act in this way is SON. So it's the first that I say, that's the dimension. In this case, we also have like a rigidity result that if x is equal to n, then we have that X is in this case homeomorphic to a torus T. The thing is that we can find, for example, fix a specific type of manifold and find that this is one. So if we have X as spherical, meaning that the universal cover is contractible, important class of manifolds, then there are ways to bound, for example, this quantity. For example, the torus is a spherical manifold because its universal cover is the Euclidean space. Then it's the dimension of the sector of the triangle. This is a very interesting question because we can ask if this is always achieved, and the answer is no. And the way that you need to construct this manifold, so the answer is no. It's really difficult. Well, all these proof that I have told you about the degree of symmetry are more geometric in the sense that we usually work with a smooth manifold and fix a metric, and then we use geometry. All these proofs are more topological in nature in the sense that we use the fundamental group and the homology and things like this. So then, just to finish already, in the study of this type of indices, there was a conjecture. So you can see that this is not trivial at all. Conjecture also. That the thing is that if you see, we always find bounds using the dimension of, in this case, topological data of the manifold. And the thing is that says that if X is a compact manifold, then we have its homology. So it tries to find a relation between, in this case, the rank and the dimension of the coefficient. In QH, because really the theory comes from the conjecture comes from rational analytical theory. That says that if we take all these, in this case, vector spaces over two and compute these dimensions, and we take the sum, then this is less or equal than 2 to the rank of X. And you might ask why we have this bound. Because if you compute this is precisely the sum that I mentioned. So, well, you can reverse it and put logarithms to say something about bounding the rank of the manifold. I think that this conjecture is from the 80s. It's still, well, it has been solved in some cases, but in general, in the general case, it's completely open in the sense that it has been proved for quite a few manifolds, but in other cases, it has been found like counterexamples if you drop one of the hypotheses. And just to make some final comments to understand this conjecture, is that because well, in this case we take the free action, then an action of TR that acts freely, and then we have a principal TR bundle that we have the inclusion of a fiber. So one may think that it might really says that the homology or the homology of the torus injects in the homology of the manifold. So the thing is that one may think that really this means that we take the sum the thing is that this is not true in general. The example usually is one, I think, on S3 by the Hopf vibration, so you see this inside the complex, and then you have the product of a complex number or a complex number of these two complex numbers here. But obviously this falls because the homology of the two spheres it's 2, so this equality falls in this case, but we don't have this equality because the sphere S3 only has homology in dimension 0 and 3, and in this case T1 is 0 and 1. It's a really subtle question that in the end, the main problem, you can translate everything that you have here in terms of a rational homotopy theory and minimal models. And the thing is that it's a really subtle question about the multiplicative structure that you have in this type of principal bundles. And I think that I have already spent some more minutes, so I will stop here. If you have any question, I'm glad to answer them.
Let me send the speaker first. Sorry, I don't know if I got your.
No.
I do have one question, maybe from way back, but
yes.
So principal G bundle is, this definition is generalizing classical bundles, right? If you take G to be
yes. So the definition of a classical fiber bundle, it's like you have the space, you have the base, and then you take the open sets, and then you have the primers here, and you have the fibers. And this is what usually it's called a fiber bundle. I mean, the notation it's not clear. There are books that use fiber bundle with the thing that I call fiber G bundle. And then this is called local trivial bundle or local trivial map. But the usual definition is here. So we can take any fiber. We don't need to have any group structure there, group action there. So the thing is that in these cases, we don't have a way to go from one chart to the other.
Well, usually, if you have maybe
I mean, if you think of the tangent line bundles or tangent bundles, then, or in this case, for example, you take the tangent bundle, then it's a fiber bundle, but it's really a fiber G bundle where G is the linear group. So yes, it's a mess of notation usually. This is why I always define fiber G bundle, so people don't think that it's a fiber bundle.
Can you hear me? Can I ask from?
Yes.
Yeah. So I have two questions. First is so if you add extra structure to your manifold, let's take Riemannian metric or a symplectic structure or anything like that, and then you consider actions that preserve that structure. Is there anything that helps you into knowing what's the symmetry of that
yes.
manifold?
I cannot say anything about symplectic structures, but indeed all the proofs that I will, or theorems that I will say for the degree of symmetry are really done by the isometrists. The thing is that if you have a compactly group acting, then you can take a metric that is invariant by this group action. So if I give you a smooth action of a compactly group on a manifold, then I always can assume that the action is by the isometrists. The thing is that it's with this particular metric. The thing is that we can use these results to find this degree of symmetry and then find that it's independent of the metric. Obviously, there's a really interesting question that is, I have a manifold and I put different types of metrics there. How big are the isometry groups there? There's a paper in the 2014 talking about this. So it's really something that it has been, at least not too much, that is starting to work in some cases.
That's clear. Thanks. And if I have time for another quick question.
Yeah.
So now looking at this piece of the blackboard in which you have all these cohomology groups,
Yes.
Does equivariant cohomology intervene in some way, or have you tried yourself?
I mean, the thing is that how does it really? Well, it's here. I put the condition of the manifold in compact. Really, the conditions that you need to have on the manifold in all the papers that this conjecture here is not clear. And we don't need the compact, we need something related with finite dimensional homology. So you can replace this, for example, for paracompact, finite dimensional CW complex. The thing is that if we have this type of vibrations, then by taking classified interspaces, then we have also this vibration, where this is precisely the Toral model. Yeah, this goes to the classified space of this, and then this is precisely the homology of this. It's the homology, is the equivariant homology of the space. So really all the conditions, and then you can reformulate the condition of the action being Thomas free. It's such that this, well, it's finite dimension. So yes, equivariant homology is like the central part of the conjecture in order to work with it.
Okay, thank you. Thank you.
Yes.
So you said that for Sn, for any n, you can always have the SO n plus 1 acting. And
yes.
Okay, and is this the only action of this dimension?
Of this dimension, yes. I mean, the thing is that the actions of Sn has been classified, I think, by Montgomery and Sanderson in the 50s, and they have like a table of all the actions that you can of, well, in this case, transitive group action, so you can move to any point of Sn. And the thing is that any group that acts then on Sn, you can put this inside SON. So yes, SON is the biggest one. And if then this works for the standard sphere, the thing is that if you only are looking at the continuous setting, you can find a homeomorphism between this sphere and an exotic sphere and translate this action of SON to the exotic sphere. This homeomorphism.
There's another question. Do these actions of a group lift to the one covered in the space?
This is an interesting question that I would say that usually no, in the sense that usually if you want to take an action and lift it to to a tori. For example, in the case of a spherical manifold, if you want to have an S1 action that you want to lift to the tori, then you need to have a fixed point of the action. And if you try to do this in the case of a spherical manifold, then you have an S1 action that has a fixed point on a contractible space, and this is impossible. So usually you cannot relieve. I mean, perhaps in the case of finite covering, something like this, you can do something like finite abstraction, but it's not something that you would generally. Well, you can try, but you will not have luck in general.
I was wondering why the time one, the group was superior there, and I was thinking that maybe it has something to do with the transformations of the universal power or something like that.
Yes.
You cannot do that.
I mean, the thing is, if I remember correctly, the proof is that if these group patterns, if you have this case G on a spherical, then if you remember, you have the evaluation map that we look in terms of fundamental groups. What you can prove is that this map needs to be injective. And if it's not, well, you can take G and comparative group and then take the maximal torus, and then this needs to be injective. Yes. So if it's not, then you can find an S1 here that maps this trivially, and you have a fixed point, and then it's what it says. Indeed, to prove this, what you do is prove that one way to do this, or it's using this fixed point, or prove that if you have a comparably group action in this type of spaces, then every finite group inside this group needs to be abelian. And if every finite group of a comparably group is abelian, then this group is also abelian. And then you have this bound, and for if it's inside, in the case of finite groups, you have this bound if the groups are trivial, so it comes on the homology or groups. So it comes from a group action here, and if not, then you have that goes to the other automorphism group. This is precisely the reason how Wormwuller construct this flat manifold that it's asymmetric. It finds something that it doesn't have any center, and its outer automorphism groups, it's also torsion free.
Okay, we shall leave further questions maybe for lunch. No, yeah, and let's stay
Yeah.
again.